All right. So, good afternoon, everyone. I'm starting today's class. So, in yesterday's class, we had learned a little bit on BGP and Intra and Inter AS routing. And this was the last slide where we had ended the class, where the question was that why should there be different Intra and Inter AS routing? So the answer to these questions were given. See, we would require different policies for both inter-AS routing as well as intra-AS routing, right? Because in inter-AS routing, the admin would want control over how the traffic is getting routed, okay, and who routes through its open network. Whereas in case of intra-AS routing, there's only a single admin and he can take control of the policy issues. And also in intra-AS routing, there will be much lesser policy issues as compared to inter-AS routing. Okay, so in order to have a hand over the complexity issues that will occur both in case of intra and inter-AS routing, um, it's always better to segregate these two. Next, of course, is the issue of scaling. So, hierarchical routing that we are using in case of intra-AS as well as inter-AS routing. So that saves the table size that needs to be advertised to different nodes for informing them about the connectivity or the connections or even advertisements of the paths to other nodes. Okay? So this will reduce the traffic update overhead. Next is the performance. So of course, in intra-AS routing, the focus can be on the performance, right? How much, whatever the routing protocol you're using, how is it performing? Okay. Whereas in case of inter-AS routing, the policy basically dominates over performance. Okay, so what policy you are using, that dominates over the performance, because that's what is basically impacting how how everything is going to perform in case of the inter-AS routing. Okay, so here in case of inter-AS routing, policy dominates over performance. So in the last class, I had told that I'll start with this routing strategy, which is hot potato routing. Okay, so the name itself is a bit peculiar. So let me start with the name itself. Okay, so what's hot potato routing and why would this name come into picture at all? So imagine you have a potato in your hand and it is quite hot. Okay, so what is your first instinct? You would simply try to just lose it out of your hand. Okay, so you will just try to keep it wherever you can keep at first. Okay, as fast as possible. So here also this same strategy is being used. Okay, so the hot potato here being the packet that you are receiving, that can be these IBGP packets, that is AS1 AS3X that path, or AS3X the other path. Okay, so let's see the example here. So we have a router here that is 2D. This 2D learns via IBGP that it can route to X via 2A, or it can route to X via 2C. That means either this path, if you can see my mouse, that is 2A to 1C, that path, or it can route via 2C directly to 3A. Okay. So this information has come to 2D via the advertisement that has been broadcast by the, or not broadcast, by the advertisement that has been sent by the router 3A to 2C, and then 2C there forwards it further to all the other routers present in its AS. Okay, so with this 2D got the information that X can be visited either via 2A or via 2C. Okay, so these are the two information that 2D has got. Now it has to take a decision, or that's what we had studied in the last class, that some policy will be taken, and according to that policy, a router takes the decision as to which path it will take. Okay, so hot potato routing basically belongs to such a policy. So what would the hot potato routing strategy say? That if you have a hot potato, just keep it wherever you can, which is as close to you as possible, as soon as possible, right? So here, a router, if it is using hot potato routing, then it will choose a local gateway that has the least intra-domain cost. Okay, that means that is uh, reachable from the given router with minimum link cost or minimum edge cost or minimum number of hops, whatever cost you are trying to consider as the edge weight. Okay, so whatever link costs minimum, that link will be used for sending the packet. But we are not going to check the entire links cost. That means we are not going to check the entire path from 2D to 2A 1C 3A or 2D 2C 3A. We are not going to check the entire path. We're just going to see the next hop routing. I mean, what is the cost or edge cost for the next hop transfer? Okay, so whichever takes the minimum next hop transfer cost, there the packet will be forwarded. Okay, so here 2D will choose 2A because as you can see the edge weight is 201 here. Okay, so that's why it has been written here that nobody is worrying about what's going to happen after that. That means nobody is concerned about inter-domain cost. We are only concerned about intra-domain cost. So whatever takes the minimum amount of edge weight, only that in the first hop, only to that gateway the transfer will be done. Okay. So that was your hot potato routing. Right? Now next is that how does BGP achieve its different policies via advertisements? Okay. So now we are going to actually look at a very real world scenario. What is the real world scenario? So suppose, see, we are having a large number of different provider networks. Okay. Now this question should have come to your mind, or at least I was expecting some question like this. See, many different network providers are there, and then customers are then getting or paying them for their network. Now, if somebody does not want, I mean, see, if we are sending the IBGP packets or routing the IBGP packets throughout the network, so that means all these advertisements are coming through some other routers. Okay, so somebody is forwarding this information to its neighbor, and then somebody else is forwarding the information to its neighbor, like that. But nobody is getting paid for that. Okay, so everybody is doing this for free. So why would a network provider do this for free? Because somebody else is getting help. That's why. So that is not, a business person would not think like that. Okay. So a business person would think that, okay, if I'm getting something in profit only, then I will do some step. Otherwise, I will not do that. So similarly, if there's a network provider and the network provider says that I don't want to forward packets to X network provider or Y network provider, so in that case, there will be an issue for actually sending the information or IBGP information or forwarding the IBGP advertisements to different um, ASS, right? So accordingly, the policies also must change, right? So we are considering currently one example here where, as you can see, X, Y, and W, these are customer networks, and A, B, and C, these are provider networks. Okay, so this is an example here. So the scenario is that the ISP only wants to route traffic to or from its customer networks. It does not want to carry the transit traffic between other ISPs. Okay. So what's the issue here? This provider ISP A, it advertises the path of its host or of its customer network W to B and C. Okay, so it advertise AW to both B and C. Now what happens? B is one service provider, which is like, why should I forward the information to anybody, any case? So B chooses not to advertise the next path to C. That means B chooses not to tell C that W can be reached via B. Sorry. So this path advertisement BAW is not advertised by B to C. Okay. Why? Because as I told you that B does not get any revenue for routing this information. Okay. So because none of C or A or W are B's customers. Okay, so B, it's not B's customers. B is not going to get any help, even if it is going to tell C or inform C that A is reachable from B. Then also that will be only helpful for communication between C and A. Right. So why should it actually go ahead and tell this thing and make its life easier? Right. So this is just basically making others' life a little more difficult than already what it is. Okay, so C does not learn the path C, B, A, and W. Now, given all this situation, how will your policy, how your policy should handle such situations? How should you advertise your IBGP paths right now? So somehow you have to ensure that C can communicate. So now C has already received information from A to C, right? So C anyways will know only one path, that is C, A, and W. Okay. All right. So now this is the scenario here, that you have A, B, C as your provider networks, X, Y, and W as your customer networks of these corresponding provider networks. Now X is one customer which is attached to two networks, both B and C. Okay. Now this is another example that we are having. So the what is the policy that is to be enforced? That X does not want to route from B to C via X. Okay. So if X does not want that, if X does not want to route any traffic from B to C via X, so X will definitely not advertise this. Okay. So X will not advertise to B that there is a route to C via X. Okay. So this is how they can take the different policies. The ISPs can take different policies. The different customer networks, they can take different policies to avoid or to achieve some long-term objective. Okay. So this is how you are basically changing the path of IBGP messages via advertisements and via taking different policies. All right. So BGP route selection. All right. So how is the route selection done? We have already known by now is that every message that is being transferred over a BGP session, it is IBGP session. So it is basically going to tell the AS path, and it will have the destination, and it is like an advertisement. But there can be many other parameters or many other parameters which will basically affect that what should be the route that should be there between a source and a destination or given AS. Sorry, source and a destination AS. Okay. So Just a second. Okay. So the router can actually route from a source to a destination AS by using a few more parameters. Basically the route can be based on the local preference value, which is nothing but the policy decision, the shortest AS path, the closest next hop router. That's what we have learned through hot potato routing, and some additional criteria that the network administrator can put on. Okay, so that's like what kind of route or what kind of cost the network administrator actually wants to bear. So that would come under the additional criteria. So today's class we are going to do something very important, and that is SDN control plane. Okay, start with this. We have already studied about what is SDN. So let's just get to that part first. So we have already studied about middle boxes, NAT boxes, and we have already also studied that with the help of middle boxes, we can implement firewalls, load balancers, NAT boxes, etc. We have also studied about OpenFlow. Here it is not given in this slide, but in the last class when we were ending data plane, after that in the starting of control plane, I think we had studied about in this control plane chapter only. We have studied about match and action pair, and we have also studied about OpenFlow, right, where we are basically the forwarding of a datagram is not only based on just the destination address but also on many other parameters which can come from different layers. Okay, so that can be done with the help of match and action pair, and that is implemented in the by using SDN and in the SDN controller that can be implemented. So we are going to see that how this is going to work. So before that, this is what we have studied until now, that we have a per router control plane, right? So that means in each router you have a forwarding table and also a given routing algorithm which will basically help to populate the content of the forwarding table. Okay, but when SDN comes into picture, then what will happen? So this is what we have studied by now. Okay, and the routing algorithm, with the help of all the advertisements that we are receiving, the routing algorithm will basically take a decision as to what should be the path that should be taken to reach a given destination. Okay, and accordingly, the local forwarding table will be populated. Alright. So we have already divided and we have already studied also accordingly. We have finished the data plane part, and now we are basically studying about the basic or the components of the control plane. Okay, we have already studied about routing algorithms, and now we are going to study about SDN. Okay, so what happens when it comes to SDN? Okay, what is an SDN control plane? So instead of having this kind of a distributed scenario where each router will also have its forwarding table, as well as the forwarding table's contents will be populated by a routing algorithm which is there at which is basically going to execute at each of these routers. Instead of doing that, we can have a remote controller based scenario where this remotely it will be computed that what should be the route for going to the given destination. So basically the routing and all that will happen at this remote controller that has been given here. So remotely all the routing will be done, and then that information will be basically given, or that information will be sent out to these routers which are there physically in the core network, and their forwarding tables will be correspondingly populated from the contents which have been received remotely. Okay. So here too you have this categorization of data plane and control plane. So the rest of this part is the data plane, and then you have the control plane here. Okay, so that means same thing, the routing and other network control or network management functionalities are going to be in the control plane, and in the data plane you have forwarding. Okay, so the question is that why we do have a logically centralized control plane? Okay? Because it will help in easier network management. It will help to avoid router misconfigurations, and it will help in greater flexibility of traffic flows. So this kind of forwarding, if you remember the OpenFlow API that we have already studied, this kind of forwarding basically allows programming routers. Okay, so when we are talking about routers doing their own forwarding and routing, etc., we are basically talking about a very small device, or just a device. Let me not call it a very small device, just a network device which is basically having, or it is basically limited by the hardware components that it has, right? Nobody is going and sitting there and programming something on that router, right? So everything is hardware based, and with that limited hardware components, we are trying to implement an algorithm and then trying to populate the contents to the forwarding table, use that contents of the forwarding table, and then forward the packet. That's quite complex there, right? So instead of doing that, if we remove this routing part or the control plane part out of these routers, then it makes it easier for everyone, right? So that's why this centralized programming concept has been proposed, and this makes it easier. So what happens? You compute the contents of the forwarding table centrally and then distribute that information to different routers. Okay? So this I've already told that distributed programming becomes more difficult. Okay? At each and every router, it becomes more difficult. So I think as you can see, I mean, you already guessed that by the name itself, we are considering software-defined networking. So there's something software related here, right? So that's what is happening at the centralized controller that we are talking about. Okay, so we have different algorithms, routing algorithms, different management functions and protocols being used there, so that not only the forwarding becomes easier, the control or management of the network functions becomes easier, but also some other objectives can also be achieved. And by other objectives, I mean that there are some other objectives that we will actually study in this course. Okay, so you have security related issues that we have already studied in Navy boxes, and we will also study here. Okay, so let's see uh, next slides how it works out. Okay, so open and non-proprietary implementation of control plane is also provided using STMs. Alright. Now, as I was telling you that why do we need SDNs? Okay, so one of the objectives is traffic engineering. Now, what's traffic engineering? We have seen so many types of engineering. We have never heard of traffic engineering, right? So traffic engineering is nothing but that keeping in mind the choices or the options or the policies that the routers in between or the ASs in between are taking, and then using those or considering those choices, making a decision for sending a packet from a given path to so a given source to destination. Okay, that's what is traffic engineering. For example, suppose there is a packet that has to be sent from a source to a destination. Source is at U, connected to U, and destination is connected to Z. Okay. So what if the network operator wants U to Z traffic to flow along this path, that is UVWZ, instead of UX, Y, and Z? Okay. So that is a decision that, that is a choice that has been taken by the network operator, and hence there has to be some kind of traffic engineering that needs to be done so that this path will be taken every time a packet is sent from U to Z. Okay. Now just imagine if you want to implement this via traditional routing methodologies, then you will definitely need a different routing algorithm in that case, where you will actually have to inform that this path cannot actually be taken, even though this may be the shortest path. Okay, so this is what is the need for traffic engineering. Okay, and traffic engineering is basically difficult with our traditional routing. So we will require some kind of SDN protocols and some strategies that we use in SDN to actually work this out. So if you remember, we have already studied about match and action pairs and open flow control, right? So those can be used here. So as it has been said here, that link weights or edge weights here, these are just control knobs. Okay, they do not give you much control. So that is to say that the link weights or edge weights are just going to say that this is where the control should go. That is, this is where the shortest path is. It is not going to control anything in this network. Okay. Now, next is another question, that is traffic. So the network operator basically wants that, okay, instead of sending it through just one, or sending the entire traffic through just one route or one path, which will basically overload that path, it's better to divide the traffic and send it over two different paths. That means all the packets will be sent via UVWZ and also via UXYZ, okay? Just to, in order to have a load balancing kind of a scenario. So for this also, you do not have a given routing algorithm. You will have to propose a new routing algorithm for this if you are trying to do it using the traditional approach. Okay. So here also SDN can be used. Now, next question. What if W, that is this router, W wants to route the blue and red traffic differently from W to Z? Okay. So in this case also, what will be required? That we actually cannot do it, okay, with the traditional routing strategies. So the answer is, as I've already told, that we can use generalized forwarding using match and action pair and SDN to to achieve any of the desired routing strategies. Okay, so that is why we are going to study a little more load balancing and many other strategies. So what's happening at the routers? At the routers, we will use generalized forwarding. Okay, we have already studied about this flow based or match action pair based or open flow. We have already studied all of these things. So these will be used in the routers here. Okay, then what we have? Then we have the control data plane separation here. which is also I have already told this in the last slides. The third part is that these are the control functions. Okay, so these control plane functions are external to the data plane switches that we are having here. Okay, they are not inside it; they are being done remotely. Okay, and routing is basically part of programmable control applications. Okay, they can be so these programmable control applications. These can be either routing, access control, load balancing, any of the other belly box features that you were talking that we had already studied, and also the examples that I was talking about, various policy decisions. Okay, now let's see here. So we have the data plane switches here, part of SDN. So what do? They are very simple, fast, and commodity switches which implement generalized data plane forwarding in hardware. Okay, so we are basically right now looking at the components of SDNs. In the data plane, very simple commodity switches are being used, which use or which implement generalized data plane forwarding in the hardware. Now, this flow or the forwarding table is computed and installed under controller supervision. Okay, what is the controller here? That's the HDN controller. All right, and what do you need? API for table-based switch control, which defines what is controllable and what is not, and we need a protocol for communicating with the controller. Okay, now let's get to the controller. That is the SDN controller, which is nothing but, if you see, it is like a network operating system. Okay, so what's happening here? It maintains network state information. It interacts with network control applications here above. That means this routing, access control, load balance, etc. Okay, so the communication or the interaction happens between the, this guy is nothing but a middleman here, the SDN controller. Okay, so it interacts with network control applications above via northbound API. Okay, so this API is basically helping to interact between these two modules, and southbound API is going to help to interact with the network switches which are below the SDN controller. Okay. Now this is implemented as distributed system for performance, scalability, fault tolerance, and robustness. Now comes our network control applications. So we have already seen this part earlier. So we have some example network control applications here, that is routing, access control, load balancing, etc. Now these are basically the brains of control that we will need to actually manage the entire network. Okay, so here all the control functions are implemented which use all the lower level services. Okay, the interaction happens of course with the help of SDN controller and northbound API. Now this entire control or the network control applications, this can be provided by a third party. Okay, now this third party will be distinct from your routing vendor, or it can be distinct from the SDN controller also. Okay, so essentially what are the components of an SDN controller? Okay, so let's see. So first part is communication, where what is the need? The need is to communicate between SDN controller and the control switches. So this is the lower part, as you can see, using OpenFlow, SNMP, etc. These are different protocols which are used. These are helpful for communicating between the control devices and the SDN controller. Then we have network-wide state management. Okay, So that is basically you want to manage the states of different devices like links, switches, etc., and different services to uh, make a distributed database. And the third layer here is the interface layer to network control applications. These are nothing but abstractions of APIs. Yeah. So now we are going to study about this lower part, the communication. Okay, so OpenFlow and SNMP and a few more stuff. So let's start with OpenFlow protocol. So the OpenFlow protocol, as we have studied, it operates between the controller and switches. TCP is used to exchange messages. Encryption is optional, depends upon what your network operator wants. There are three classes of OpenFlow messages. So the communication that's happening between this controller and the switch, okay, using OpenFlow protocol, that is done using three classes of OpenFlow messages. One is controller to switch, another is asynchronous, that is switch to controller, and and the third one is the symmetric, which is miscellaneous. Okay. So this is of course different from OpenFlow API. All right. Why? Because API basically specifies the generalized forwarding actions, okay, that we were talking about earlier, right? The generalized forwarding actions that are to be taken at each of the routers in the data plane. But here that's not happening. Here we are basically trying to control or trying to communicate between the controller and the switches in the data plane. So controller to switch messages. So key controller to switch messages has some features. Okay, some key features are that controller queries, they switch features, and I mean basically we have switch features and switch replies. Configure. So the controller queries or sets switch configuration parameters. And of course, there's modify state messages, which are for adding, deleting, modifying flow entries in the flow tables, etc. Okay. So these will be basically the key controller to switch messages. You have features, you have configure, and you have modify state messages. And then you have the packet out message, which is nothing but here the controller can send the packet out of a specific switching port. Now we are going to look at key switch to controller messages. So the first one is packet in, where we transfer packet to controller. Then we have the flow removed packets, which will just, in this case, the flow table entry is deleted at the switch. Okay, so this information is basically sent using the switch to controller messages. Then we have the port status, which will inform the controller of a change on a port. Okay. So what's there? So here, fortunately, network operators don't program switches by creating or sending OpenFlow messages directly. Okay, what do? They use higher level abstraction at controller to have all these kind of controls. Okay, that is creating or sending flow messages. So let's see an example of a controller data plane interaction. Okay, so as an example, Dijkstra link state routing is being used as the routing algorithm here. So what's the first step? S1 is experiencing link flow. Okay, sorry, link failure, not flow. So S1 is experiencing link failure and it uses OpenFlow port status message to notify the controller about this situation. Then what happens? The SDN controller receives this OpenFlow message and updates the link status info. Right? Then what happens? Given all this information, now Dijkstra routing algorithm is being used here, right? So what will happen when this information reaches to the next module? So here Dijkstra's routing algorithm application, it was previously registered to be called whenever link status changes, right? So the link status has now changed because of the link failure. So now this algorithm will be called again in order to get the latest routing information given this new update that has come about the network. So the extra will now compute the new route. Okay. Now the route has been computed. Then this link state routing application will interact with the flow table computation component in the SDN controller. You can see this module here, the flow tables component. This is for flow table computations. So this will compute new flow tables, okay, whichever are needed. Because if I mean whatever flow table is basically required to be updated. So accordingly, the new flow table needed will be computed, and then the controller will use OpenFlow to install new tables in switches that need updating. Okay, so this is how an interaction happens between control and data plane in SDN. Okay, now what are the challenges that can be there in case of SDNs? Okay, so of course the control plane task becomes complex. Okay, why? Because all of the tasks are happening, all the most important tasks are happening in the control plane. It has to be dependable, reliable, its performance has to be scalable, and it has to be secure for a distributed system. Okay, so what are the needs? There should be robustness to failures. That means some strong theory of reliable distributed system for control plane must be used. And of course, dependability and security must be there. So network protocols meeting mission specific requirements. So nothing but real time, ultra reliable and ultra secure protocols need to be used. And of course, we are considering this or we are going to use it for a very large scale scenario, okay, millions and billions of hosts. So the scaling should be beyond the single AS, right? And of course, when we are actually trying to work out with 5G right now, which is having a lot more usability, a lot more data rate that it provides, and also with this, a lot more complexity also comes up. Okay, so when it comes to 5G, SDN is actually quite critical. It plays a very significant role if it is used in 5G. Okay, so what are in this slide? Just a comparison between SDN and future of traditional network protocols that has been done. Okay, so what's basically happening here? So with respect to forwarding tables, okay, so SDN computed forwarding tables and forwarding tables which are computed in the routers. Okay, so this is one example of logically centralized computed versus protocol computed forwarding tables. Now just imagine the scenario of congestion control. Okay, so when we were having congestion control in our traditional networks or traditional networks where routers were actually having distributed control, in that case what was happening, whenever there was congestion, we used to have different types of methods to actually find out that there is congestion in the scenario, right? It could either, the congestion could be informed to the source either by the network routers or by the source, sorry, by the destination itself. Okay, that's what we had studied in TCP also, if you remember AIMD. Okay, but when it comes to SDN, the controller will send the sender rates based on router reported congestion levels, right? And this will become, if you want to implement in SDN also, then how the evolve, I mean, how it will evolve, and if you want to implement all of these features in traditional network protocols, then how you will evolve all these features. So these are questions that are still, under research. Okay, which one is better to use? Because if something is centralized and it is software based, etc., it does make life easier, like SDN is making the life easier, but it also has its own complexities and challenges that comes with. Okay, so we have already studied that what are the challenges that we have to go through if we want to use SDN, and on top of that, security also is a very big challenge. Okay, so given this, in the long run, which one will be better? So that's still a question that needs an answer. So now we are going to get to the next module of this course. We have already studied about ICMP, so I will just go through very quickly through this. So what is ICMP? It is Internet Control Message Protocol, which is used by hosts and routers to communicate network level information. And what's that network level information? It can be error reporting, it can be echo request and reply, and it can be any other, I mean, many other services that ICMP actually provides. Okay, so ICMP messages are carried in IP datagrams. Okay, so what does a message actually consist of, or what is the format of this ICMP message? It has a message type, or ICMP message type, then a code, and then the first 8 bytes of the IP datagram that is causing the error. Okay, so you can see that corresponding types and codes and the descriptions of what do they actually mean, right? So that's what will be the content of an ICMP message. Now, Traceroute is just an example of ICMP, and let's see what Traceroute actually does. I am very sure all of you are aware of what is Traceroute. Okay, and many of you may have used Traceroute by now. So basically, we are going to find out that whether a given packet is reaching a given destination or not, and how it is reaching, what path it is taking. Okay, so what happens in case of Traceroute and ICMP? The source sends sets of UDP segments to destination. Right. First set has a time to live for one. Second set has a time to live for two. This is hops. Okay. So like that, the datagram in the nth set, it arrives to the nth router. Now, what does the router do? The router discards the datagram and sends the source ICMP message type 11 and code 0. Okay, let's see what's type 11. Type 11 is that TTL has expired. And then ICMP message will pass. Also, ICMP message can include names of the router and IP addresses. When the ICMP message is arriving at a source or has arrived at a given source, then the RTTs are recorded. So this is what is happening. 3 probes are happening each time, and this will keep happening until the UDP segment eventually arrives at the destination host, or the destination returns ICMP port unreachable. That is, the message type is 3 and the code is 3, and otherwise if the source stops. Okay. Now, we were talking about the control plane functions, right? When we were talking about SDNs, and one of the functionalities is network management that we were talking about. Right, so why do we need a network management? We have several ASs, and these ASs are basically interacting with each other and with different hardware and software components. Okay, so that is the reason why we need some kind of a management system for this. Okay, so what is the definition of network management? So as per the definition which is there in Kuros and Ross also, if you can check the book, Network management includes the deployment, integration, and coordination of the hardware, software, and human elements to monitor, test, poll, configure, analyze, evaluate, and control the network and element resources to meet the real-time operational performance and quality of service requirements at a reasonable cost. So this is the given definition of network management and what are the tasks that it includes. So basically all the management functionalities related to a network and its coordination with other networks is what network management includes, right? So what are the components of network management? Okay, so there should be a managing server, okay, and there are managed devices or which are known as agents. Okay, they are equipments with manageable or configurable hardware and software components. And then there is data, which basically consists or contains the state or configuration, or it is the operational data, or it is device statistics. Okay, so please remember these components of network management. We will be needing them, or we will see them just right afterwards. Then we have the network management protocol, which basically makes use of all of these components in order to control the entire set of tasks that are going on within a network. Okay, so this protocol is used by managing servers to query, configure, manage devices, which are used by devices to and manage devices, and it is used by devices to inform managing server of data events. Now, what are the different management techniques that or management protocols that a network operator uses? Okay, so there are a few. We are going to see a few of them, a handful of them here. So first is command line interface or CLI. Okay. So the problems with this strategy is that we have operator issues. Okay, that is what is the type, what is the script, etc. And this is direct to the individual devices. Then we have SNMP or MIB. SNMP is Simple Network Management Protocol, which uses MIB, which is Management Information Base. Okay, so SNMP uses MIB, which is MIB is also the list of what is the list of text or data that is going to be useful to achieve the objectives laid out by SNMP. Okay, so SNMP or MIB is a management protocol that is used by network operators, and you have netconf or YANG. We will also study about netconf and YANG also. So this gives a more abstract and network-wide and holistic approach for management of traffic or network. It emphasizes on multi-device configuration management, and it uses YANG, which is a data modeling language. And with netconf, one can communicate YANG compatible actions or data to or from or among different remote devices. So yeah, it's already 2:55. So I will get to SNMP protocol in the next class. Meanwhile, if you have any questions, please feel free to ask. I'll stop the class here.
Hello, ma'am. Am I audible?